Welcome to this fascinating lesson on droplet solidification after flow. Today we're going to explore a remarkable phenomenon where droplets that behave as liquids inside channels can spontaneously gel or solidify when they exit. The core idea is simple but profound. Motion fluidizes, stopping solidifies. Let me explain what this means. Inside a channel or tube, droplets experience continuous shear forces that keep them in a liquid state. The molecules are constantly being rearranged by the flow. But when the droplet exits and the flow stops, something remarkable happens. The removal of shear stress allows the internal structure to reorganize, and the droplet can transition from liquid to gel or even solid. Here's a visualization. The droplet flows smoothly through the channel as a liquid, but once it exits and the flow ceases, it rapidly transitions to a solid or gel state. So why does this happen? What's the underlying physics? Let's dive into the mechanisms. The key concept is shear-induced structuring. During flow, the shear forces actually prevent the formation of stable intermolecular networks. Shear stress continuously disrupts any molecular organization that tries to form. It keeps breaking apart bonds and preventing particles from settling into fixed positions. When the shear is removed, suddenly these molecules are free to interact and form stable networks. This is especially important for colloidal suspensions and polymer solutions. Let me give you an analogy to make this crystal clear. Imagine a marching band on a football field. When the band is marching, everyone is moving in an organized pattern. They maintain spacing and move together. This is like the flowing droplet, where shear keeps everything moving. But when the music stops, the band members naturally cluster together in groups. They form stable configurations. This is exactly what happens when the droplet exits and solidifies. Now let's look at the mathematical framework that governs this phenomenon. We need to understand shear rate and viscosity. The shear rate gamma dot is defined as the velocity gradient. It measures how quickly velocity changes perpendicular to the flow direction. Inside a channel, the shear rate is high because of the velocity differences between the center and walls of the channel. For a channel, we can estimate the shear rate as the average velocity v divided by the channel radius r. After the droplet exits, the shear rate rapidly drops to nearly zero. This is the trigger for solidification. Here's an important question. What determines whether solidification actually occurs? Not all fluids exhibit this behavior. The answer lies in a dimensionless number called the Deborah number. This number compares two timescales. The Deborah number equals the relaxation time divided by the process time. The relaxation time is how long it takes for the material to restructure. The process time is how long the flow lasts. If the Deborah number is much greater than 1, the material doesn't have time to relax during the process, so it behaves like a solid. If the Deborah number is much less than 1, the material has plenty of time to relax, so it behaves like a liquid. During flow in the channel, the process time is long, making the Deborah number small. The material flows as a liquid. After exit, the process time drops dramatically. The Deborah number shoots up, and the material transitions to solid-like behavior. Let's work through a concrete numerical example using a polymer solution to see these concepts in action. Consider a polymer droplet flowing through a microfluidic channel. Let's assign some realistic values. The channel radius is 50 micrometers, which is typical for microfluidic devices. The average flow velocity is 1 millimeter per second. The polymer has a relaxation time of 0.1 seconds. This is how long it takes for the polymer chains to restructure after being deformed. Let's calculate the shear rate during flow in the channel. Shear rate equals velocity over radius. That's 1 millimeter per second divided by 50 micrometers. This gives us 20 inverse seconds. This is a moderate shear rate. Now, let's find how long the droplet spends in the channel. Suppose the channel is 1 centimeter long. The process time is length divided by velocity. That's 10 millimeters divided by 1 millimeter per second, giving us 10 seconds. Now we can calculate the Deborah number during flow. D during flow equals 0.1 divided by 10, which is 0.01. This is much less than 1. Since the Deborah number is much less than 1, the material behaves as a liquid during flow, exactly as we expected. After the droplet exits, the shear stops almost instantaneously. The relevant time scale becomes the relaxation time. The Deborah number after exit effectively approaches infinity because the process time drops to nearly zero while the relaxation time stays at 0.1 seconds. The result is rapid gelation or solidification. The polymer chains that were kept apart by shear now quickly form a network structure. Let me give you another powerful analogy. Think about traffic flow on a highway. On the highway, cars flow smoothly. Everyone maintains speed and spacing. This is like the droplet flowing through the channel with continuous shear. But at a traffic jam, cars suddenly cluster together and stop moving. This represents the solidification after exit when shear is removed. What types of materials commonly exhibit this droplet solidification phenomenon? Let's explore several important examples. First, colloidal suspensions, where particles have attractive interactions. The flow keeps particles separated, but stopping allows aggregation. Second, polymer solutions above a critical concentration. The polymer chains entangle and form networks when shear is removed. Third, hydrogels that are shear thinning. They flow easily under stress but gel when the stress is removed. Fourth, biological fluids such as blood or mucus. These contain proteins and cells that can aggregate when flow stops. Let's talk about viscosity and how it changes during this process. Viscosity is the key parameter that indicates the transition. For non-Newtonian fluids, viscosity ET is a function of shear rate. It's not constant like it is for simple fluids like water. Many of these materials are shear thinning, meaning their viscosity decreases as the shear rate increases. The Corot model describes this behavior. Eta of gamma dot equals eta 0 times 1 plus lambda gamma dot squared to the power n minus 1 over 2. Here eta 0 is the zero shear viscosity, lambda is a time constant, and n is the power law index. During flow, the high shear rate reduces the viscosity, making the droplet easy to flow through the channel. After exit, as the shear rate drops to zero, the viscosity increases dramatically, sometimes by several orders of magnitude. This is what causes the apparent solidification. Let's estimate how much the viscosity can change using realistic parameters. Suppose the zero shear viscosity is 1,000 Pascal seconds. This is very thick, almost solid-like. The power law index n is 0.3, indicating strong shear thinning behavior. The time constant lambda is 1 second. During flow, the shear rate is 100 inverse seconds. Using the Corot model, the viscosity during flow is 1,000 times 1 plus 10,000 to the power negative 0.35. This works out to approximately 10 Pascal seconds. That's a 100-fold reduction from the zero shear value. After exit, as the shear rate approaches zero, the viscosity returns to its zero shear value of 1,000 Pascal seconds. That's a 100-fold increase. This enormous viscosity change from 10 to 1,000 Pascal seconds explains the dramatic liquid-to-solid transition observed experimentally. Here's another important question. How fast does this solidification process occur? Is it instantaneous or gradual? The answer is that it depends on the material's relaxation time. This is the characteristic time for internal structure to reform. The solidification time is approximately equal to the relaxation time. For our earlier example, that was 0.1 seconds. For some materials, like certain colloidal gels, the relaxation time can be just milliseconds. Solidification is nearly instantaneous. For other materials, like concentrated polymer solutions, relaxation times can be seconds or even minutes. The transition is more gradual. This phenomenon has numerous practical applications across different fields. Let's explore some of them. First, 3D bioprinting. Bioinks are designed to flow through printer nozzles, but then rapidly gel after deposition to maintain the printed structure. Second, drug delivery systems. Injectable hydrogels flow easily through needles, but solidify in the body to provide sustained release of drugs. Third, food processing. Many food products like ketchup or mayonnaise are shear thinning. They flow when squeezed but hold their shape on the plate. Fourth, industrial coatings. Paints and coatings are designed to flow during application, but quickly set to prevent dripping or sagging. Working with these materials presents several challenges that engineers and scientists must consider. One major challenge is clogging. If solidification begins before the droplet fully exits, it can block the channel. Another challenge is controlling the exact timing of solidification. This requires careful tuning of material properties and flow conditions. Ensuring reproducibility is critical. Every droplet must behave the same way for reliable manufacturing or medical applications. Let's discuss an advanced concept that's crucial for understanding solidification: the yield stress. The yield stress, denoted tau y, is the minimum stress required to make the material flow. Below the yield stress, the material behaves as an elastic solid. It can deform slightly but won't flow. Above the yield stress, the internal structure breaks down and the material flows as a liquid. During flow in the channel, the applied shear stress exceeds the yield stress, so the material flows. After exit, there's no applied stress, so the material is below its yield stress and behaves as a solid. When the applied stress tau is less than the yield stress, the material is solid-like. When the applied stress exceeds the yield stress, the material is liquid-like. The Herschel-Bulkley model combines yield stress with shear thinning behavior to give a complete picture. The equation is stress equals yield stress plus K times shear rate to the power n. Here K is the consistency index and n is the flow behavior index. This model captures both the yield stress behavior and the shear thinning behavior we've been discussing. Let me leave you with one final analogy that beautifully captures this entire phenomenon: a chocolate fountain. In a chocolate fountain, the chocolate flows smoothly as a liquid. The constant motion from the pump keeps it fluid. But if you turn off the fountain and let the chocolate sit, it solidifies into a block. The same material transitions from liquid to solid based on whether it's flowing or at rest. Let me summarize the key concepts we've covered in this lesson. The fundamental principle: motion keeps materials fluid by preventing structure formation, while stopping allows solidification. The mechanism is shear-induced structuring. Shear disrupts molecular networks during flow, but allows them to form when flow stops. The Deborah number, comparing relaxation time to process time, predicts whether a material will behave as liquid or solid. For shear thinning materials, viscosity can change by orders of magnitude as shear rate varies. This phenomenon has critical applications in bioprinting, drug delivery, food processing, and industrial manufacturing.